Landslide Vulnerability Zone by Weights of Evidence Model using Remote Sensing and GIS, in Kodaikanal Taluk, Tamil Nadu, India. Abstract: Incidences of landslides are common in India. According to Geological Survey of India, approximately 0.49 million km2 or 15% of land area of the country is vulnerable to landslide hazard, of which 0.098 million km2 is located in the northeastern region and the rest 80% is spread over Himalayas, Nilgiris, Ranchi Plateau, and eastern and western Ghats. GSI, 2006. The area selected for the study, Kodaikanal Taluk, is located within the high landslide-prone zone, where debris slides, soil slips, and rock slides are a major threat for the population living in this area. The present study is the assessment of landslide vulnerability using Weights of Evidence Model in Kodaikanal Taluk, Tamil Nadu. In the first stage, landslide locations were identified in the study area from interpretation of high resolution of cartosat data and Google Maps, and field surveys. In the second stage, 10 data layers are exploited to detect the most vulnerable areas. These factors are tin, aspect, slope, geomorphology, land use, soil, distance from roads, distance from lineament, distance from streams, rainfall. Next, landslide vulnerable areas were analyzed using the Weights of Evidence Model and mapped using landslide conditioning factors. Keywords: remote sensing, GIS, weights of evidence, landslide, Kodaikanal Taluk. Introduction. Landslide is a mass wasting which denotes any downslope movement of soil and rock under the direct influence of gravity, and a disaster that can potentially affect the general quality of life in very many ways. These are complex phenomena, whose time-space distribution results from an interaction of numerous factors such as geological, geomorphological, physical, and human. Varnes, 1978, Crozier, 1986, Cruden and Varnes, 1996. The devastating effect of landslide, causing irrevocable loss of property of billions of dollars and terminating the invaluable life of loss of thousands of people and cattle as well, and injuring our equal number every year, makes landslide in natural systems are of the most fearful natural hazards at global level. Crozier and Glade, 2005. Chung et al., 1995. Make a pointed observation that the worst affected are the developing countries, wherein occur 95% of the landslides, causing an annual loss of 0.5% gross national products. The International Landslide Center of the University of Durham recorded in 2007 that the most seriously affected country was China with 695 landslide-induced deaths, followed by Indonesia, 465, India, 352, Nepal, 168, Bangladesh, 150, and Vietnam, 130. 89.6% of the fatalities worldwide were caused by landslides triggered by intense and/or prolonged precipitation. Other triggering processes were construction, mostly undercutting of slopes, 3.4%, mining and quarrying, 1.8%, and earthquakes, 0.7%, while no cause would be identified for 3.4% of the landslides. Petley, 2008. Study area. Study Area 1. The Palani Hills are an eastward spur of the Western Ghats with a maximum east-west length of 65 km, and a north-south width of 40 km with a total area of 2064 sq.km. Kodaikanal, located at latitude 10.13 n, longitude 77.32 e, is situated in Palani Hills, and Kodaikanal Taluk is spread over 1050 sq.km. The foothills to 800 m consist of thorn forest at the lower range and then dry deciduous forest typical of peninsular India. Submontane evergreen forest accompanied by shrub savanna can be seen up to 1600 m. From 1600 m to 2000 m, the outer montane slopes are characterized by grassland savanna and shola forests. The upper part of the hills is undulating plateau interspersed with occasional peaks rising to c. 2,500 m. Area 385 sq.km, average altitude 2,200 m. The upper montane Grasslands are interspersed with shola forests. Nilgiri tar, Hemitragus hylocrius, the state animal of Tamil Nadu, can be seen in the upper reaches. Materials and method. The studies cited above have been used for WO objectives and expert-informed subjective methods. The study began with the preparation of landslides inventory map-based extends field work, a previous inventory map and satellite images. Furthermore, the following 7 possible landslide-causing layers. The methods identified for the present study are weights of evidence, WO, with the following parameters: rainfall, slope, aspect, elevation, road, soil drainage, lineaments, geomorphology, land use/land cover. Were analyzed for landslide susceptibility mapping using weights of evidence, WO. Weights of evidence, WO, is based on the observed associations between allocation of landslides and each associated factors of landslide occurrence to display the correlation between landslide locations and the parameters controlling landslide occurrence in the area. Lee, 2005. Cartosat, 2005, 5.3 m resolution, IRS P6 List 3, 2005, 30 m resolution and IRS List 4, 2009. 5.8 m resolution. Satellite data products were used as the primary data sources for the present study, collected from National Remote Sensing Agency. Survey of India topographical maps bearing serial numbers 58F7, 8, 11 and 12 1:50,000 scale published in 1969 and 1:25,000 scale published in 1994 were used to extract base map features. Landslide Inventory Map. Landslide inventory mapping is the systematic mapping of existing landslides in a region using different techniques such as field survey, air photo/satellite image interpretation, and literature search for historical landslide records. A landslide inventory map provides the spatial distribution of locations of existing landslides. The landslides in the study area were determined by comprehensive field surveys. The landslides, which are currently indefinite in characteristics and boundaries, were identified using old dated satellite images. As a result, the satellite images were very useful in determination of landslides inventory map. Yeltsin and Bulut, 2007. In this study, the susceptibility mapping started with the preparation of an inventory map of 213, total pixel 4095, landslides from field studies, a previous inventory map, and satellite image analyses from cartosat image. Weighting of geomorphology. Geomorphology is considered as an important factor closely related to landslide occurrence because geomorphological units are created on the integration of the topological characteristics, geological structures, geotectonic movements, and morphometries. Geomorphology map for Kodaikanal was collected from SWA at scale 150,000. The Kodaikanal is characterized by colluvial fills, bajadas, deeply dissected defection slope, less dissected plateau, moderately dissected plateau, pediments, valley fills and others. Colluvial fills forms 35% of the watershed. Next to it, valley fills occupies 21% of the Kodaikanal. Weighting of slope. The slope of the study area ranges from 0 degrees to 50 degrees. In general, the steeper the slope, the easier it is for gravity to initiate a landslide. Slopes are classified into 6 classes according to the gradients that represent terrain morphology, such as gently sloping, 0-10 degree, undulating, 10-20 degree, moderately steep, 20-30 degrees, steep, 30-40 degree, and very steep, 40 degree 50 degree, and 50 degree. Slope angle has a positive effect in the range between 20-50 degrees based on the positive weighted contrasts. Slope range in class 20 degree 30 has the most significant spatial association with landslide occurrence. Weighting of elevation. Altitude or elevation is another frequently used conditioning factor for landslide susceptibility analysis. In the present study, the DEM of the study was obtained from topographic maps in 1:50,000 scale with a contour interval of 20 m. The elevation of the study area ranges from 500 to greater than 2000 m. The elevation values were divided into 5 categories by using an interval of 500 m. Elevations 0-500 m display some negativities association with landslides. The elevation between 500 and 2000 m shows a positive association with landslide occurrence. Aspect is the horizontal direction to which a mountain or hill slope faces, which is expressed clockwise, from 0 to 360 degree. In terms of aspect, flat or non-orientated areas have a negative spatial association with landslide occurrence. In other landslide susceptibility assessments, Abdallah, Koroaz, Bukir, and Kali, 2005, Lee and Dan, 2005, Lee and Talib, 2005, that have investigated aspect, south-facing slopes were found to be most susceptible to landslides. Aspects are grouped into 9 classes such as flat north, northeast, east, southeast, south, southwest, west, and northwest. Weighting of land use/land cover. Land use is the factors related to the effects caused by human activities on landslide occurrence. The study area is covered mainly by forest and wastelands, a lesser extent of grasslands and residential areas mainly in the form of small settlements occupy the study area. By using IRS images, the land use map of the study area was produced and then boundaries were determined in conformity with field visit. In terms of land cover classes showed agriculture land and water bodies in negative weighted contrasts. Built-up land, wasteland, and forest showed the positive contrast value. Many of the landslides in hills occur by the erosion associated with drainage. The hilly area is drained by perennial and non-perennial streams. It flows in the northern part of the study area. The study area depicts dendritic drainage pattern, which is the most common, and looks like the branching pattern of tree roots. Proximity to drainage is derived from drainage map with buffer zones on either side of the drainage lines. It is categorized into 6 classes, in meters, 0-50, 50-100, 100-150, 150 to 200, 200 to 250 and more than 250, Table 4.19. As higher stream buffer negative is W and their relation to the occurrence of landslides is not clear. One of the controlling factors for the stability of slopes is road construction activity. The Ghats road may represent a barrier or a corridor for water flow, a break in slope gradient, or, in any case, may tempt instability and slope failure mechanisms. The widening of the road is a possible triggering factor and source of landslide vulnerability. The distance from the road is computed as the minimum distance between each of the cells and the nearest road represented in vector format. The distance to roads is calculated in meters and divided into 6 classes such as 0-100 m, 100-200 m, 200-300 m, 300-400 m, 400-500 m, and 500 m. Distance from road between 0-500 m displayed a positive contrast value, while distance 500 m showed a negative contrast value. The road between 0-100 m shows a positive association with landslide occurrence. To classify road network proximity, buffer analysis was applied. This study uses multiplied distance. Weighting of lineament. The lineament was extracted from IRS images. Proximity, buffers, to these structures increases the likelihood of occurrence of landslides as selective erosion, and movement of water along structural planes promotes such phenomena. Lee 2007, Pradhan et. al. 2009, Pradhan 2010. The buffer of the lineament as follows, in meters, 0-100 m, 100-200 m, 200-300 m, 300-400 m, 400-500 m, and 500 m, Table 4.21. Distance from fault between 100 to 500 m displayed a negative contrast value, while distance 500 m showed a positive contrast value. Results show that lineament between 0 to 100 m have a strong relationship with landslide occurrence. Weighting of rainfall. The mean annual precipitation in Kodaikanal ranges from 132 mm over lowlands to 1,238 mm over highlands. Rainfall distribution map was produced using an empirical equation that relates altitude to the mean annual rainfall over the Kodaikanal Taluk. Rainfall value from 900 to 1200, greater than 1200 showed a positive contrast value and others showed a negative contrast value. The highest contrast value determined in the rainfall classes was class rank greater than 1200. The second highest was class 900, 1200. Soil in the study are sandy clay loam, loamy sand, clay loam, and others. Table 4.23. Nearly 56.5% of the total area has sandy clay loam. The soil cover in the study area is shallow and varies from a minimum depth of 70 cm in the proximity of Vilpatti to a maximum of 126 cm in the extreme southeastern part of the study area near Iyeragonam. The soil texture represents the relative proportions of sand, silt, and clay. The term texture refers to the size of the individual soil particles and has nothing to do with the amount of organic matter present in the soil. It has been observed that the soil affects the landslides mainly through these two soil characteristics. High groundwater conditions occurring in sandy soils may liquefy the masses resting on the slopes during an earthquake. This can cause a landslide on a slope even as gentle as 10 to 20%. Weights of evidence model. In this study, the weights of evidence modeling was used for the large-scale landslide susceptibility mapping. The weights of evidence model has many advantages compared to the other statistical methods. Weights of evidence is a data-driven method that is basically the Bayesian approach in a log-linear form using prior and posterior probability and is applied where sufficient data are available to estimate the relative importance of evidential themes by statistical means. Bonham-Carter 1994. The weights of evidence modeling use the Bayesian probability approach and were originally designed for mineral potential assessment. Bonham-Carter, 1988, Bonham-Carter, 1994. This method was also being applied in landslide susceptibility mapping in the past 1 decade. Lee et al., 2002, Van Westen et al., 2003, DeHull et al., 2008 and Regmi al., 2010. If F represents the presence and F represents absence of a potential landslide factor and if L represents the presence and L represents absence of landslide, then WO method calculates the positive and negative weights of the respective factor classes based on the probability ratios. Bonham-Carter, 2002, as follows. For each factor positive weight, W+, indicates the presence of spatial association between conditioning factor, F, and landslides, L, while the magnitude of this weight indicates the positive correlation between the presence of the predictive factor and the landslides. A negative weight, W, indicates an absence of the spatial association between predictive factor, F, and landslides, L, while the magnitude shows the level of negative correlation. The weight contrast values were assigned to each respective class within each of the predictive factor thematic layers in ArcGIS 10 using raster calculator. The resulting weighted raster layers were added together to obtain a raster layer of the landslide susceptibility index. Slope plus, aspect plus, elevation plus, geomorphology plus, lineament plus, land cover plus, drainage plus, road plus, soil plus, rainfall. D:\map final \correction \way result natural.jpg. The result of WO modeling is a probabilistic map based on evidence of landslides. Weights calculated individually for the 10 parameters to produce estimated evidence. Different weights can be summed by using the natural logarithm of odds called logit. In this case the contrast C equals W plus W, gives a measure of spatial association between the predictors and landslides. Yannick Theory et al. 2005. Calculations of values of W and W for all selected variables used to calculate the posterior probability, update the prior probability. When multiple predictors are combined, areas that have a weight higher or lower respectively correspond to a greater or smaller probability of finding the landslides. Local knowledge of the landslide susceptibility in the Kodaikanal Taluk suggested 10 binary predictor patterns of topography, namely, soil, geomorphology, slope, aspect, elevation, streams, lineament, road, rainfall and land cover, which are useful evidence for predicting landslide vulnerability. Each of the landslide-related factors, the weights and contrast, were calculated using the weights of evidence method. The total number of pixels in the study area was 114,3160, and the total number of landslide occurrences was 4,095. All the controlling parameters by giving different weight age value for all the themes. The final LVZ map is prepared and categorized into very high, moderate, and low vulnerability zones. Low 8.3% of the area, which contains 41.4% of the observed landslides, has a high landslide vulnerability. 16.9% of the study area, which has 33.9% of the observed landslides, has a high landslide vulnerability. 38.4% of the study area has a moderate landslide vulnerability, which contains 19.8% of the observed landslides. 6.03% of the study area which. The accuracy of the final LVZ map is evaluated on the basis of the observed landslides. First, the final LVZ map is checked by overlaying with the observed landslide map. 187 of the 213 observed landslides are good predicted, and only 26 of the total landslides are wrongly predicted. The LVZ map with the observed landslides indicating the different levels of prediction. Most of these areas, which are situated in Vadakavunji, Aduksam, and Perumalmalai, have verified conditions of slope, geomorphology and elevation, but some key features are noticeable as, slope angles are normally higher than 20 degrees, and predominantly, higher than 40 degrees. All wrongly predicted landslides occurred mainly in Pishalur, Periyur. These areas have various unfavorable conditions for landsliding. Conclusion: 4 different classification methods were used to classify landslide vulnerability index into susceptibility classes: low, moderate, high, and very high. Natural break classification method gave the best result. 60% of the landslides fall closer to the road, authenticating the relationship between landslide and proximity to the road. The Kodaikanal areas close to road and the erosion of the bank of removal of support is one of the main processes responsible for landslides. Landslides are frequent in areas roadsides. Majority of the landslide have occurred close to high-order streams, and hence, the incipient erosion taking place in the hills is one of the reasons for slope failure.